So this is one of the most important mindset that shift about our views in PyTorch. So in the previous videos we have is most models we built probably looks like linear architecture. Like if we have the input, there's a layer after the layer and another layer and then output. That is sequential. That style is called linear architecture. But and usually we use the NN that's sequential. That works perfectly. But real deep learning systems are often not linear. And in the modern days or modern architectures, it takes multiple inputs, produce multiple outputs, reuse the same layers multiple times, and choose different paths dynamically. And it create layers on the fly. So that's where custom architectures become essential. And here's the core idea of custom architectures. So the big idea is in PyTorch, our model is just Python code. We are not trapped inside a fixed graph. We can use if, for, loops, dictionaries, lists, conditions, multiple returns, shared objects, and dynamic creation. Inside forward. So that's flexibility exists because PyTorch uses a dynamic computation graph. So PyTorch builds the graph during execution and not before. So every forward pass can be different. This is one of the biggest reasons why PyTorch became popular for research. Why NN sequential eventually becomes limiting. So NN that sequential is basically having a layer 1, layer 2, layer 3, and the sequence linear architecture. That's good for simple pipelines. But what if we need two inputs? Branching, reusable encoders, conditional execution, loops, dynamic depth. Sequentially, this is sequential cannot naturally express this. That's why we create our own model. So class my model and then that module, and manually define the forward. So modular design reminder. So the modular design meaning builds reusable blocks as separate and then modules instead of writing giant messy models. So yeah, and we have multiple objects like convolutional block or models. So this matters because advanced architectures become complicated. Reusable blocks help maintain readability, debugging, scalability, and organization. So let's talk about the four custom architecture patterns. So we have four major patterns. First is multiple inputs and outputs. Second, parameter sharing. Next is conditional execution. Next is a dynamic model creation. These are extremely common in real deep learning systems. So first is multiple inputs and outputs. So the problem is, suppose our system receives an image and metadata. Example of the metadata is the location, shutter speed, timestamp, weather. These are different data types. We should not process them identically. So here's the correct design. We create one branch for images and one branch of metadata, then combine them later. So the architecture idea first is we have the image and the metadata, and they have different paths. So the image, they have the encoder, the metadata encoder, and later on we combine those in the shared layers, and then prediction. This is called multimodal learning because multiple data modalities are combined. So why this is better? The model learns relationships between modalities. Example, maybe blurry nighttime images behave differently depending on metadata. The network learns that jointly. So PyTorch makes this easy. So we could have the accepts multiple inputs. Next is multiple outputs. We can also return multiple outputs. we could return the scene prediction and lighting prediction. This is common in multitask learning. One shared feature extractor solves multiple tasks. Example, we have the input images predicts object class, depth, segmentation, lighting, and pose. And simultaneously, training multiple outputs, we compute multiple losses. So we compute multiple, then use the backward. One backward pass updates everything together. So here's a key insight. So PyTorch allows arbitrary input or output structures because forward is just a Python function. We are not restricted to one tensor in and one tensor out. Next is parameter sharing. This is one of the most important ideas in modern deep learning and inspired by Siamese network. So the problem is, suppose we want to compare two images, image A and image B. So the question is, are these the same products, person, or object? We need to encode both images into feature vectors. So this is wrong approach. Let's say we have the encoder 1 and build the encoder 2. Why? But even if architectures are matched, weights are different, gradients are different, training diverges, eventually encoder 1 feature space is not equivalent to encoder 2 feature space. Comparison becomes unreliable. Correct approach, use one encoder object twice. We have the self encoder and encoder. Then we have the feature 1 and feature 2. So we use that one encoder object twice. Here is the parameter sharing. This is parameter sharing. Same layers, same weights, same representation. Why does matter? Now both images map into the same features map. So the goal is we could have those both images and we could map them into the same feature maps. So we could calculate their relationships, their distance to each other. That consistency is critical. This is foundation of Siamese networks. From the image 1 and image 2 share the same encoder and compare. We use interface verification, signature matching, image similarity, and product matching, metric learning. So important concept is calling the same module twice. The encoder and another encoder again, the same. It does not create new weights. It reuses the same parameters. Next is gradient flow. Both images contribute gradients to the same encoder. So the encoder improves using both examples. That extremely powerful. Next is conditional execution. This is where models make decisions during execution. So the idea is different inputs may need different computation. Example is the image shallow processing, hard noisy image deeper processing. Next is sequential, cannot do this naturally. Sequential always runs sequence in linear from layer 1, layer 2, and layer 3 every time, no decision making. Next is PyTorch solutions. We use the ordinary Python code like conditional if statement, and that's it. So and different inputs can take different paths. Yeah, that's a kind of example of condition. So here's a big question: how does backpropagation work if only one branch run? This is where PyTorch dynamic graph becomes critical. Dynamic graph explanation here is each forward pass builds a new graph. If input takes branch A, then the graph will have a branch A graph. If next input takes branch B, then branch B graph. The graph will take the branch B. So PyTorch records only operations that actually happen. Then perform the backpropagation. We could perform it by tracing the backward through that graph only. After backward, the graph is discarded. Next forward starts fresh. So this is extremely powerful. It enables adaptive computation, routing networks, mixture of experts, recursive models, tree structured networks, and many research architectures. Next is dynamic model creation. This is about building architectures programmatically. So the problem, suppose we want 2 layers, 4 layers, and 10 layers, depending on a hyperparameter. We do not want to write or rewrite the model every time. So the first attempt is we use the list comprehension is the Python and append the layers we wanted. But this fails because a normal Python list does not register modules. PyTorch cannot track them. The Python cannot track them because it doesn't have the dynamic computation behind. So modeled parameters won't include them. So the meaning optimizer won't update them, saving won't include them, and training breaks. So the correct solution is we use this module list and ended module list. So we use the and ended modules. We have the and included in the layers. Now PyTorch knows these are real trainable layers. So model so now model depth is dynamic by using that, using the list comprehension, using this module. So PyTorch tracks modules only if assigned as attributes inside module list, inside module dictionary, and inside sequential, not ordinary Python containers. So NN module dictionary is like a dictionary for layers. So it's like a dictionary in Python and useful for multitask systems, name branches, and configurable architectures. Why dynamic creation is important. So modern deep learning often involves hyperparameter search, configurable architectures, neural architectural search, scalable systems, and dynamic creation lets us build models programmatically. So the most important big picture here is there's no magic happen here. The PyTorch feels powerful because models are not Python programs. We are not writing into a rigid graph definition language. We are simply writing Python code, and PyTorch dynamically tracks tensors operations. That's the heart of PyTorch, of their dynamic track tensors operations, because it could we could be more flexible because of dynamic computation that traces the operations and tensors. So here's the model summary. So the pattern, like multiple inputs and outputs, is different branches and tasks, and parameter sharing is same module reused multiple times, and conditional execution is different paths for different inputs, and dynamic creation is architecture built programmatically. So one of the famous architecture is Siemens Networks. It uses shared encoders. Transformers is repeated shared blocks, and mixture of experts is conditional routing, and multimodal AI is multiple inputs. Multitask learning is multiple outputs, and ResNets is custom graph connections, and recursive nets is dynamic execution. So modern AI would be impossible without these patterns. So in the past videos and past discussions, we learned that PyTorch is from the layers, forward, loss, and backward, sequential, and linear. But now, a neural network is a programmable computational graph, and is not could be not rely only on linear.